Hi there, this is question 1 that I've given you on cars and trailers, looking at F equals MA with combined objects. So here we have, if you get the question in front of you, we've got a car and a trailer. And first thing I'm going to do is translate that into a diagram because there isn't one. So we've got a car and a trailer, and these only need to be as accurate as you want to make them. If you want to make it look like a car and a trailer, that will help you remember which one's which, but you can use 2 rectangles, 2 blobs, whatever you want. I am going to put on, we've got the mass of the car and we've got the mass of the trailer given, and we're on a horizontal road. So what we're looking at with these questions, we're really only working in one dimension. We could look at the forces that are working vertically, so we'd have the weight of the car versus the reaction, the normal reaction of the road. But actually it's in equilibrium this way. It doesn't tell us anything new. So these questions are all about the horizontal forces. So horizontal is what we're looking at for this one. So what forces are going on here? Well, in the question we've got quite a few forces given. We have the driving force on the car. Let's just have a little look. The bottom sentence, the driving force on the car due to its engine is 2,380 newtons. So that is going to be, just going to change colour here, the force this way, so 2,380 newtons. And then there's these resistive forces, and they're different. And this resistance is coming not perhaps from the road, but from the engine and the wheels and the bearings, and the car. So respectively means that the car has that 630 resistance and the trailer has 280 resistance. So let's put those on as well. Now, this one is our 630. That's on the car, and we also have resistance, so going in the opposite direction to motion, 280 newtons there. Okay, so I'm also going to draw an arrow somewhere above it, just a normal arrow, to say I'm moving this way. And of course, if we're in equilibrium here, then my movement will be a constant velocity. But if we're not in equilibrium with all our forces, then we're going to get an acceleration, and that's the whole point. This is all going to be about F equals ma. So there is a force that I've missed out in there, which, if we look at the system as a whole, is not so important. But if we are going to look at these two things separately, then if we ignore the trailer, and you can just literally cover it up with a piece of paper or your hand, or I'm going to just move my screen across. If we just look at the car and what's going on for the car, it's got a force pulling it forward, its own drive. It's got a resistive force, but the trailer is also providing some resistance. So there is a force in here because we're tugging this trailer along. We don't know what that is yet, so we're going to label that with a T, tension in the tow bar. And because our tow bar is light and inextensible, what that means, it doesn't really do anything itself. But if we ignore the car now, cover that up, and just look at the trailer, all we've got is a force backwards on the trailer. That can't be right because it's definitely moving forwards just as the car is. So what's pulling it along is, yep, the tension in the tow bar. So it's the tow bar is pulling the trailer and it's holding back the car. So this is where we look at the two things separately. Okay, however, part A says find the acceleration of the car. Now, acceleration of the car, because this is a rigid tow bar, is going to be the acceleration of the whole system. So what you might have seen is a little double arrow to say, well, we think it's accelerating that way. So it could be it's slowing down if all these forces that are resisting are greater than the driving force, but I suggest that we potentially are going forward and accelerating forwards as well, so speeding up. So for the general acceleration, because it's the same for both, we could look at the whole system as one unit. So what that means is these T's in the middle, the tensions, cancel each other out. We don't need to worry about those. We can imagine that it's one rigid system, as if we'd attached the car and the trailer just back to back, or front to back, and it was one unit. So you can always draw yourself a little separate diagram. If I stick the three wheels on it, you can get the idea of what I mean. So the forces on this are 2,380 forwards, and the forces that are holding it back are the 630 from the car and the 280 from the trailer. So this is our force diagram. The tensions, because they work in opposite directions, cancel each other out. So that's what I need to do F equals ma with. And so I know what force I've got. So F equals ma for this. My force is 2,380 minus 630 and minus 280. That would be my net force on the whole thing. And on this side, well, my mass is now the whole mass, so it's both things added together. So 1,400 plus 700, which makes 2,100 kilograms. That's my mass times my acceleration. So this is the net force or resultant force. That's the mass, and that's acceleration. So you can see we've just got a load of numbers in there and then A, so I can work out what A is. Okay. So 2,100 A equals 2,380. Get the calculator out. $2,380 minus 630 minus 280 gives me 1,470, and A, if I divide that by 2,100, I get 0.7 meters per second Okay, so that's the acceleration. So we just looked at it as a whole system for that one. However, part B is going to involve looking at the tension in the tow rope. And I'll stop this video after part B because for the second part we're going to be using, for the third part, part C and part D, we're going to look at SUVAT. So the tension in the tow rope, which we've called D, well, for this one, if we look at the system as a whole, we kind of ignore T. So we're going to either have to look at the trailer on its own or look at the car on its own. And we know the acceleration. I'm going to, tempting to look at the car, but I'm going to just look at the trailer because I've only got two forces on the trailer. I've got three on the car. So for the trailer, start with the simpler one. What's going on? Again, we're going to do F equals MA. The force that's pulling it forwards, well, that's T. And then we've got a resistance of 280, so it's going to be minus the 280. So let's write that down. We've got T for the trailer, T minus the resistance 280, that's the net force, equals its mass is 700 kilograms and its acceleration, well, we worked that out just before, 0.7 meters per second. It's 0.7. So T minus 280 is this, 490, I make that. So T itself is 490 plus 280. Quite a big tension, as you'd imagine, for this situation. That's 770 newtons. If I'm going to make a mistake, it would be here, so just double check that. Cool. So we could have done that by finding it in the car. We would have got the same result to show you. If we consider what's going on for the car, again, for its forward acceleration, there it is, there's the car, we'd have 2,380 minus 630 minus T as well, be the net force. So we've got 2,380 minus 630 minus T would equal, mass is now 1,400 for the car, times 0.7. So we could work it out like that. That would give us 1,750 minus T equals, don't know that one in my head, 1400 times 0.7, 980. So T equals, if I flip that over to that side, 1750 minus 980, we should get the same. Yep, we do. 770 newtons. So this is where we look at them separately, as if we want to find this tension in the tow rope, we have to look at one or the other object. If we're looking at the acceleration of the whole system, we can kind of combine. And so for part B, we looked at one or the other. So separate systems. And sometimes we need to do both. If we have two unknowns, for example, we might end up with simultaneous equations here that we can put together. In this case, we had enough information to use one or the other. Okay, hope that helps get you started on cars and trailers, and speak to you soon. Take care, bye.